The first warning is not a wall of ice. It is the silence of a changed wind. Across the northern continents, autumn lingers less each year. Spring arrives late, and snow survives in hollows where meltwater once ran freely. Grasslands pale beneath dust, rivers carry colder water, herds alter their routes. Far beyond the horizon, snowfields that once vanished in summer begin to remain, season after season, until white ground becomes hard blue ice and the ice begins to move. It does not advance like an army in a single visible charge. It grows by accumulation, by pressure, by centuries of snowfall that fail to disappear. Valleys fill, mountain glaciers thicken, vast sheets spread outward across Canada, Greenland, northern Europe, and the highlands of many continents. The planet is not buried beneath one continuous frozen shell, but its climate is being reorganized by ice on a scale no living person can comprehend. Before we go deeper, take a moment to like the video and subscribe, if this is the kind of history and mystery you enjoy. This transformation unfolds over thousands of years, not in one sudden catastrophe, by the broad interval known as the Last Glacial Maximum, roughly between 26,500 and 19,000 years before the present. The great ice sheets of the northern hemisphere approach their largest combined extent of the last glacial cycle. Their growth is uneven. Some margins push forward while others pause or retreat. Mountain glaciers reach local maxima at different times. Iceland, Patagonia, the Alps, the Himalayas, New Zealand, and lesser ranges develop their own histories of expansion and decay. What survives in the record suggests a world connected by cold, yet never uniform. A valley in southern Europe may hold scattered woodland while open tundra dominates another region at the same latitude. Parts of Australia become cooler without becoming universally drier. Tropical forests contract in some areas, persist in refuges elsewhere, and change composition rather than simply disappearing. Even the average temperature hides more than it reveals. Global surface air may be around 5 to 6 degrees Celsius colder than today, but that number is not a description of any single place. Continental interiors can be far colder, especially in winter. Oceans cool less dramatically. Some tropical regions experience modest temperature declines, but profound shifts in rainfall, seasonality, vegetation, and river flow. The difference between land and sea matters because climate is not a blanket laid evenly over the globe. It is a moving system of winds, currents, moisture, dust, snow, and heat, all redirected by enormous masses of ice. The Laurentide ice sheet spreads over most of Canada and reaches into the northern United States. To the west, the Cordilleran ice sheet covers mountain systems along the Pacific side of North America, sometimes merging with Laurentide ice and sometimes remaining separated by corridors that open and close. Across the Atlantic, the Eurasian complex covers Scandinavia, the Baltic region, parts of Britain and Ireland, and extends into the Barents and Kara seas. Greenland is locked under a far larger burden of ice than today. These sheets rise high enough to alter the atmosphere flowing over them. They deflect winds, reshape storm tracks, change where snow falls, and create cold, dry regions far beyond their visible margins. Beneath their weight, the crust of the earth bends downward. Around their edges, land is pushed into broad peripheral bulges. Rivers are diverted, basins deepen, existing drainage systems are blocked by ice, creating lakes that can remain stable for centuries before escaping in sudden floods. Yet the scale of the transformation is easiest to grasp far from the ice itself, at the edge of the sea, Water locked in glaciers is water removed from the oceans. Shorelines retreat across continental shelves. In many regions, the sea lies more than 100 meters below its modern level. Plains appear where fishing boats now cross deep water. Islands become peninsulas. Peninsulas become parts of continents. The Bering Land region connects Northeast Asia and Northwest North America. Sunda joins much of western Indonesia to mainland Southeast Asia. Sahul expands around Australia and New Guinea, though deep-water crossings still separate it from Sunda. Patagonia broadens toward the Atlantic. Coastlines familiar to us do not yet exist. These exposed lands are not empty strips of mud waiting to drown. They contain river valleys, grasslands, wetlands, dunes, hunting grounds, camps, and migration routes. Entire human landscapes now lie beneath modern seas. Their absence distorts the archaeological record, because many communities likely preferred coasts, estuaries, and river mouths, exactly the places later erased by rising water. The map of surviving sites is therefore not the map of where people actually lived. It is the fragment left above the flood line. The atmosphere itself carries the signature of this colder age. Dust concentrations rise sharply. Dry surfaces expand. Sparse vegetation leaves soil exposed to powerful winds. Fine particles travel across continents and oceans before settling into ice, lakes, and seabeds. Greenland ice preserves some of this dust grain by grain, recording shifts in distant sources and circulation patterns. On open plains, dust settles over snow, animal tracks, and abandoned hearths. In some regions it accumulates into thick loess deposits that will later become fertile soil. Still, the cold does not create a dead planet. South of the ice margin stretches a mosaic of steppe, tundra, shrubland, woodland refuge, desert, and seasonal grassland. Mammoths, horses, reindeer, bison, woolly rhinoceroses, and saiga antelope move through open environments rich enough to sustain immense herds. Predators follow them. Humans follow both prey and opportunity. Fire burns in shelters. Stone is worked. Bone and antler are shaped. Clothing becomes more effective. Roots are remembered across generations. The last glacial maximum is severe, but severity is not the same as emptiness. That is the first contradiction of this frozen age. The ice sheets close in, yet life does not simply retreat before them. It reorganizes. Some populations move south or toward lower ground. Others remain in protected valleys, coastal plains, tropical refuges, or highlands once assumed to be uninhabitable. The evidence remains incomplete, but it already shows that human responses are regional, inventive, and unpredictable. There is no single story of collapse, no universal migration, and no one line separating survival from disappearance. The real mystery begins there, between the simplicity of the ice on a map and the complicated world beneath it. From a distance, the period appears white, cold, and still. Up close, it is full of movement, glaciers grinding over rock, rivers changing course, tides crossing unfamiliar shelves, forests shrinking into sheltered pockets, dust rising from exposed plains, animals tracing ancient paths, and people learning the limits of places that seem determined to reject them. The cold is not merely background, it becomes an architect, rebuilding the planet one season at a time. The cold becomes an architect, but it leaves no written plan. To reconstruct what happened, researchers must read materials that were never intended to preserve history bubbles trapped in ancient ice. Grains of pollen buried in lake mud, shells formed in vanished seas, dust carried across continents, and shorelines now stranded above or below the modern coast. None of these records speaks alone. Each preserves only part of the climate, and every part must be dated, compared, and interpreted before the frozen world begins to take shape. Ice cores provide clear evidence because snow can accumulate year after year, compressing into layers that hold chemical traces of the atmosphere above them. In Greenland and Antarctica, drills descend through hundreds or thousands of meters of ice, recovering cylinders whose deepest sections formed long before the last glacial maximum. The ice contains variations in oxygen and hydrogen isotopes, ratios influenced by temperature, moisture source, and the route a storm followed before the snow fell. It also contains wind-blown dust, sea salts, volcanic particles, and air bubbles sealed as loose snow became solid ice. Those bubbles preserve samples of ancient atmosphere, allowing scientists to measure past concentrations of carbon dioxide, methane, and other gases. Yet an ice core is not a simple thermometer. The relationship between isotope values and temperature changes with geography, season, elevation, and atmospheric circulation. Greenland records conditions in the North Atlantic region, but it cannot represent the whole planet. Antarctic ice reveals a different rhythm, often smoother and influenced by southern hemisphere processes. The two can be aligned through abrupt changes in atmospheric gases or volcanic markers, but uncertainty remains in the exact dating of older layers. Scholars still debate the timing and regional expression of some events, particularly when one archive suggests a change began centuries before another appears to respond. Beyond the ice sheets, ocean sediments extend the record across much of the globe. Tiny marine organisms build shells from minerals dissolved in seawater. When they die, their remains settle onto the seabed, forming layers that can survive for tens of thousands of years. The chemistry of those shells reflects water temperature, salinity, global ice volume, and local ecological conditions. Oxygen isotope ratios are important. When continental ice sheets grow, they store water enriched in the lighter oxygen isotope, leaving the oceans relatively enriched in the heavier form. Shells formed in those oceans record the shift, but the signal combines temperature and ice volume, so separating one from the other requires additional evidence. Other marine clues include the species living in each layer, molecules produced by certain algae, the size and composition of mineral grains, and fragments dropped from melting icebergs. Together they reveal that the oceans were cold, but not uniformly frozen or stagnant. Deep water circulation continued. Some water masses in the northwest Atlantic remained relatively warm and salty compared with the surrounding glacial ocean. This surprising persistence matters because ocean currents move heat around the planet and influence the stability of ice sheet margins. Beneath the obvious drama of white continents, the sea continues its slower, less visible work. On land, pollen offers another kind of map. Flowering plants release enormous numbers of grains, each with the shape characteristic of its plant group. Some grains settle in lakes, peatlands, caves, and sheltered basins, where they become part of accumulating sediment. By identifying pollen in layers, researchers estimate which trees, grasses, shrubs, and herbs grew nearby. The result is not a perfect photograph. Wind can carry pollen far from its source. Different plants produce unequal quantities, and some environments preserve it better than others. Even so, networks of pollen sites reveal changes impossible to see from isolated fossils. Across Europe, northern Africa, and the Middle East, Pollen shows colder and often much drier winters during the last glacial maximum. Open vegetation expanded, but woodland did not vanish everywhere. Sheltered valleys, coastal zones, and favourable slopes retained trees in places once portrayed on older maps as nearly treeless. These refuges become crucial later, when warming allows forests to spread outward again. The discovery also warns against treating broad biome maps as hard boundaries. A label such as steppe or tundra can conceal riverbank woods, protected pockets, and local environments where both animals and people find resources unavailable on the exposed plain. Lake sediments add charcoal, algae, insect remains, mineral dust, and changes in water chemistry. Cave deposits contribute layers of calcite whose isotopes reflect rainfall and vegetation above the cave. Coral terraces and fossil reefs record sea levels in tectonically stable regions. Raised beaches, drowned river channels, and sediments from continental shelves show where coastlines once lay. Along the Atlantic coast of Africa, hundreds of screened indicators suggest relative sea level continued falling through much of the glacial maximum, though the exact depth varied from place to place because the crust itself moved under changing loads of ice and seawater. This movement complicates every ancient shoreline. Global sea level may have stood roughly 100 to 125 meters below the present, but no coastline experienced that change in precisely the same way. Land beneath the major ice sheets was pressed downward. Regions around them rose in response. Farther away, gravitational changes caused by the shrinking attraction of ice masses altered local water levels. Reconstructing a coast therefore requires models of ice volume, earth structure, sediment movement, and tectonics, not merely subtracting a single number from a modern map. Mountain glaciers provide another set of clues, especially where no continental ice sheet existed. Moraines mark glacier edges. Scratched bedrock records the direction of moving ice. Boulders transported far from their source can be dated through isotopes produced when rock surfaces are exposed to cosmic radiation. A global compilation published in 2026 assembled evidence from more than 15,000 glacier reconstructions across 271 mountain ranges. It shows both the reach of glaciation and the uneven timing of local maxima. Some glaciers reached their greatest extent before the global peak. Others remained large after major northern sheets had begun changing. That unevenness is not an inconvenience to be smoothed away. It is one of the central facts of the period. The last glacial maximum is a scientific framework, not a single frozen day. Different archives respond at different speeds. Ice sheets may continue advancing after temperature begins to shift because their immense mass reacts slowly. Vegetation can change within decades, while coastlines move over centuries. Ocean circulation can reorganize before the atmosphere displays the full effect. The picture emerges only when these imperfect records overlap. Ice remembers air, shells remember water, pollen remembers landscapes, dust remembers wind and dryness, moraines remember the reach of glaciers. None preserves the entire world. Yet together they reveal a planet whose cold was measured not by silence, but by thousands of subtle traces still waiting in the ground. The world revealed by those scattered traces is not simply colder than the one we know. It is physically larger in some places, compressed in others, and almost unrecognizable along the margins of the continents. The first transformation is measured in water. As snow accumulates over northern lands and mountain ranges, vast quantities of ocean are transferred onto the continents and stored as ice. The sea falls slowly, generation after generation, until coastal shelves emerge into daylight. Rivers extend their courses across plains that no longer exist. Bays become valleys. Islands join larger land masses. Harbours of the modern world would stand far inland, while familiar coastlines lie beyond the horizon. The exact amount of sea level fall varies by location and method, but a global decline of roughly 100 to 125 metres captures the scale. Even that number can mislead if imagined as a bathtub draining evenly. The crust beneath the great ice sheets sinks under their weight. Regions around them rise in broad peripheral bulges. The gravitational pull of the ice itself draws seawater toward frozen continents, so when ice later melts, local sea level may initially behave in ways that appear counterintuitive. Every shore has its own history, shaped by ice, gravity, tectonics, sediment, and the flexing of the solid earth. Across North America, the Laurentide ice sheet dominates the continent. It covers most of Canada and reaches deep into the northern United States, filling basins, burying ridges, and redirecting drainage on a continental scale. Its surface rises into an elevated frozen plateau that changes the path of the jet stream and intensifies cold conditions far south of the ice margin. To the west, the Cordilleran ice sheet spreads through the mountain chains of western Canada and Alaska. At times, the two systems approach or meet, sealing routes between the Pacific coast and the interior. At other times, gaps appear, but their timing and habitability remain subjects of close debate. Greenland carries a thicker and more extensive ice cover than today, though its own history is complex. Across the North Atlantic, Iceland is almost entirely glaciated. Modelling suggests that its ice may reach the edge of the continental shelf during its local maximum around 24 to 21,000 years ago. Some extreme reconstructions even allow the possibility of extensive ice connections toward Greenland, though no single model fully settles the question. The important point is that local glacier maxima do not occur everywhere at precisely the same moment. The planet enters a broad glacial peak, but each ice body responds to regional snow, temperature, ocean conditions, and topography. Farther east, the Eurasian ice sheet complex spreads across Scandinavia, the Baltic Basin, northern Germany and Poland, parts of Britain and Ireland, and the shallow seas of the Arctic margin. Ice occupies regions now divided by the North Sea and Baltic Sea, because those basins are altered by lower water levels and immense glacial loading. The Scandinavian centre of the ice sheet rises high enough to influence storms crossing Europe. North of it, ice extends across the Barents and Kara sectors, though the geometry of these margins changes through time. Britain is not one simple frozen island. Northern and western zones lie under ice, while southern areas remain exposed, cold and often windswept. South of the continental sheets, mountain glaciers enlarge through the Alps, Pyrenees, Caucasus, Himalayas, Andes, and many smaller ranges. Their valleys become corridors of ice, and their terminal moraines mark the farthest reach of glacier tongues. Yet the new global database of mountain glacier extents reveals enormous regional diversity. Some tropical mountains support glaciers much larger than today because cooler temperatures lower the snow line. East African peaks, the high Andes, and mountains of New Guinea hold ice despite their latitude. This is one reason the phrase frozen world must be used carefully. Ice reaches into the tropics at altitude, but vast tropical lowlands remain ice-free, experiencing cooler temperatures, shifting rainfall, and changing vegetation rather than continental glaciation. In South America, the Patagonian ice sheet stretches along the southern Andes. It is not merely a passive response to cold. Its height and shape alter the regional atmosphere, redirecting westerly winds, changing precipitation, and strengthening sharp contrasts across the mountains. Moist air rising on the western side releases snow and rain, while the eastern side lies in a pronounced rain shadow. Storm tracks shift around the ice mass. The glacier therefore helps create the climate that sustains parts of it, even as it deepens aridity elsewhere. Patagonia also extends farther east because the Atlantic shelf is exposed, creating broad coastal plains where tides and estuaries function very differently from today. The sea between continents is transformed as well. Beringia becomes a vast region linking northeastern Asia and northwestern North America. But it is not a narrow bridge. It includes plains, river systems, low hills, wetlands, and cold steppe environments extending across what is now the Bering Strait. Far to the southwest, the Sunda Shelf connects mainland Southeast Asia with Sumatra, Java, Borneo, and surrounding lands. Rivers cross the exposed shelf toward a distant coast. Sahel joins Australia, New Guinea, and Tasmania into a single larger continent, although deep channels still separate Sunda from Sahel and require deliberate sea crossings. These exposed worlds become habitats, migration routes, and centres of human life, most of which are later erased beneath rising seas. The oceans shrink in area but do not become motionless. Continental shelves narrow or vanish in some regions, changing tides, coastal currents, and the exchange of water between shallow and deep basins. On the Patagonian shelf, lower sea level reorganizes tidal energy across a coastline displaced far from its modern position. In the North Atlantic, sea ice expands seasonally, but open water regions remain. Deep water continues to form, and some northwestern Atlantic waters remain relatively warm and salty compared with the surrounding glacial ocean. Beneath the severe surface climate, circulation persists in a pattern more complicated than a simple shutdown. The land itself carries the scars of this new arrangement. Ice scrapes bedrock, excavates basins, transports boulders, and grinds stone into flour-fine sediment. Rivers dammed by glaciers spread into enormous lakes. Frozen ground expands across wide belts beyond the ice margin. Repeated freezing fractures exposed rock. Dust storms lift sediment from dry floodplains and deposit it thousands of kilometers away. The result is a planet remade not only in climate but in shape, with altered mountains, redirected rivers, displaced seas, and landscapes created by the weight and movement of ice. From any one human camp, these changes are too slow to witness as a single event. Yet over centuries, coastlines recede, valleys narrow beneath glaciers, and familiar routes become impossible. The world does not end. It changes its geometry, quietly and relentlessly, until survival depends on learning a map that never stops moving. Beyond the margins of the great ice sheets, the exposed world is not necessarily warm. The frozen fronts act like walls in the atmosphere, steering winds, redirecting storms, and draining moisture from regions thousands of kilometers away. South of Laurentide and Eurasian ice, belts of tundra and steppe spread across terrain that now supports forests, farms, and cities. The ground freezes deeply in winter. Summer warmth is brief and often too weak to melt the lower layers of frozen soil. Water gathers above permafrost, creating seasonal wetlands beside expanses so dry that dust can rise from river plains and travel across oceans. This landscape is often called the mammoth steppe, but the name can create a false image of one continuous grassland stretching from Western Europe to Beringia. In reality, it is a shifting mosaic. Productive meadows occupy some valleys and flood plains. Dry grass and herbs dominate exposed uplands. Dwarf willow and birch survive in protected hollows. Sedges gather around shallow water. Patches of bare ground interrupt the vegetation where frost, wind, and trampling prevent plants from establishing. The balance changes with latitude, elevation, soil, snowfall, and grazing animals. A place rich enough to support herds in one century can become sparse after a change in drainage or persistent snow cover. The air is frequently dusty. Greenland ice records concentrations far above those of the later Holocene, showing that the glacial atmosphere carries vast quantities of particles. Some dust comes from exposed continental shelves and dried riverbeds. Some rises from cold deserts in Central Asia and other continental interiors. Stronger winds lift it because vegetation is thin and precipitation removes it less efficiently. The sky is not permanently dark, but haze is common during powerful wind events. Dust settles on snow, darkening its surface, and on grasslands where it gradually forms deep loess deposits. Much later, those deposits will become fertile agricultural soils. Europe beyond the ice is colder and generally drier than today, especially in winter. But it is not a treeless wasteland everywhere. Pollen recovered from dozens of sites reveals a more complicated geography. Open steppe and tundra dominate large areas, yet trees persist in refuges around the Mediterranean, the Balkans, parts of Italy, the Iberian Peninsula, and sheltered pockets farther north. Pine, birch, juniper, oak, and other species survive where local moisture, slope direction, or protection from wind creates favourable conditions. Older reconstructions often drew sharp boundaries between forest and open land. The pollen suggests blurred edges, isolated stands, and woodland corridors that matter greatly to animals and humans seeking fuel, shelter, edible plants, and workable wood. The Mediterranean is not simply a warm refuge. Winters can be severe. Rainfall patterns shift, and uplands hold snow for long periods. Sea level is lower, so coastal plains extend outward, but many modern islands remain separated by water. River valleys cut across exposed shelves toward distant shorelines. In some areas, reduced evaporation and changed storm tracks maintain moisture. In others, aridity intensifies. Evidence remains incomplete because many lowland archives now lie beneath the sea, and surviving pollen records are unevenly distributed. Still, they show that local topography often matters as much as latitude. Northern Africa presents another contrast. The Sahara is generally drier than during later humid phases, but it is not environmentally identical across its breadth. Mountain massifs create cooler zones and catch limited moisture. River systems fed from distant regions continue to shape corridors. Around the Mediterranean coast, steppe vegetation expands, while parts of the Nile basin and other water sources remain critical lifelines. Farther south, tropical belts shift as rainfall zones move. Grasslands, savannas, woodlands, and forests contract or reorganize rather than responding in one direction. Human groups here do not experience the last glacial maximum as an advancing ice wall. They experience changing water availability, altered plant communities, modified animal ranges, and the need to know where reliable habitats persist. Across the Middle East, colder winters and reduced precipitation transform uplands and plains, but again the pattern is uneven. The Levant contains ecological gradients compressed into short distances, from coast to mountain to interior steppe. Springs, caves, river valleys, and woodland pockets become anchors in a landscape of greater seasonal stress. Farther east, high plateaus and deserts face intense cold, strong winds, and limited moisture. The boundary between habitable and inhospitable ground can move with a slight change in altitude or exposure. A south-facing slope may lose snow early, while a shaded valley remains frozen. Central and Eastern Asia contain some of the harshest continental conditions. Vast interiors cool strongly because they are far from the moderating influence of oceans. Permafrost expands, mountain glaciers descend, and deserts produce dust carried toward the Pacific and Greenland. Yet river basins, lake margins, and protected valleys remain productive enough for animals and people. In East Asia, pollen and sediment records show cold, dry conditions near the end of the glacial maximum, including near the lower Yangtze, but vegetation shifts with elevation and proximity to water. The exposed continental shelf enlarges eastern China, while coastlines move far beyond their modern positions. Sahul offers one of the clearest warnings against global simplification. Mainland Australia is cooler by several degrees on average, but rainfall does not decline uniformly. Climate models show regional differences in circulation, while archaeological and environmental evidence indicates that lower temperatures reduce evaporation in some areas. A place can receive less rain, yet retain moisture longer because water disappears more slowly from soils and pools. Some regions become more arid, but others maintain a positive moisture balance sufficient to support stable human occupation. Grasslands expand in certain zones, forests retreat in others, and alpine environments grow colder. Tasmania, joined to the mainland by exposed land, lies within a larger southern continent shaped by powerful winds and altered ocean boundaries. South America is equally varied. The Patagonian ice sheet dominates the southern Andes, intensifying wet conditions to the west and deepening the rain shadow to the east. Farther north, Andean glaciers expand at high elevation while tropical lowlands remain ice-free. Cooler temperatures may reduce evaporation, changing lake levels even where rainfall decreases. The Amazon forest does not vanish as one unit. It contracts, fragments, or changes composition differently across regions, with debate continuing over the scale of open vegetation and forest refuges. The Last Glacial Maximum is therefore not one climate but a system of connected climates. Ice sheets alter winds. Winds move dust. Dust affects soils and snow. Lower seas reshape coasts and currents. Mountains divide rain from dryness. Vegetation survives in pockets that broad maps overlook. Beyond the frozen frontiers, the struggle is rarely against ice alone. It is against uncertainty whether the next valley holds wood, whether snow will linger, whether a spring will fail, and whether a route remembered from earlier generations still leads through a living landscape. The living landscape takes shape first as movement. Across the open country south of the ice, dark lines appear on the horizon and slowly resolve into herds. Mammoths travel in family groups, their shoulders high beneath dense coats, their tusks curving forward through cold air. Horses move in tighter bands, alert to wind and predators. Reindeer cross valleys in long seasonal migrations. Bison, musk oxen, saiga antelope, wild sheep, and woolly rhinoceroses occupy different parts of the same immense ecological system. From Western Europe through Northern Asia and into Beringia, large herbivores turned frozen ground into a shifting pasture. This world is often imagined as barren, but the abundance of animals demands a more productive explanation. The mammoth steppe is cold and dry, yet in many places it supports grasses, sedges, herbs, and low shrubs rich in nutrients. Long summer daylight allows rapid growth. Snow cover can remain thin because precipitation is limited and strong winds sweep exposed ridges. Thin snow matters. Herbivores can paw, scrape, or push through it to reach plants below. In regions where deeper snow accumulates, access to food becomes difficult, and even cold-adapted animals may struggle. The severity of winter is therefore measured not only by temperature, but by whether the ground remains reachable. Mammoths are central to this ecology not simply because of their size, but because they alter the land around them. They knock down shrubs, strip bark, break branches, trample snow, disturb soil, and open pathways through vegetation. Their dung returns nutrients to the ground. Herds moving repeatedly along the same routes help maintain open habitats that favour grasses over dense woodland. Bison and horses add their own pressure through grazing and trampling. The result may be a feedback system in which large herbivores help preserve the very steppe that feeds them. Scholars still debate how strong this effect was, but the animals are not passive occupants of the landscape. They are engineers within it. The woolly mammoth is especially well suited to the cold. A thick outer coat covers a dense underlayer of wool. Fat stores insulate the body, while small ears and a short tail reduce heat loss. Its blood chemistry includes adaptations that help oxygen function at low temperatures. Tusks can sweep snow aside, strip bark, test surfaces, and serve in competition. Yet the mammoth is not invulnerable. Its enormous body requires large amounts of food. A prolonged period of deep snow, ice crust, drought, or declining vegetation can create serious stress. Adaptation allows survival within a range of conditions. It does not abolish limits. Woolly rhinoceroses carry a different form of power. Their broad front horns and massive shoulders suit open, cold terrain. Wear on fossil teeth and preserved stomach contents indicate diets dominated by grasses and herbs, though local feeding varies. Their bodies conserve heat, and their low-slung heads are well positioned to reach ground vegetation. Unlike mammoths, they do not spread across all of Beringia into North America. Their distribution reflects ecological history, barriers, and timing rather than a simple inability to endure cold. The absence of a species from one region can be as informative as its presence elsewhere. Reindeer are more mobile and flexible. Their seasonal movements link tundra, steppe, river crossings, uplands, and sheltered wintering grounds. Broad hooves support them on soft terrain and help clear snow. Their antlers, coats, and digestive systems suit environments where food quality changes sharply through the year. For human hunters, reindeer provide meat, fat, hide, sinew, antler, and bone. But the relationship depends on knowledge of migration routes. A herd passing through a valley can sustain a community for a time. A missed migration can leave that same valley empty. Horses thrive in many open glacial landscapes because they can process large quantities of coarse vegetation and travel efficiently across broad ground. Their teeth preserve microscopic wear and chemical signatures that reveal differences in diet and movement. Bison graze in productive steppe and riverine zones, while saiga antelope favour dry open country. Musk oxen endure extreme cold, but are less widely distributed than popular images suggest. No single animal represents the entire mammoth steppe. The community changes from one region to another and from one millennium to the next. Predators follow this abundance. Cave lions range across Eurasia and into parts of North America, hunting large and medium-sized prey. Wolves operate through cooperation, testing herds for weakness and opportunity. Brown bears occupy varied habitats, while cave bears depend heavily on plant foods and use caves for hibernation. Spotted hyenas extend far into Eurasia during colder periods, carrying bones into dens and competing with humans for carcasses and shelter. In North America, short-faced bears, American lions, dire wolves, and other predators occupy glacial and periglacial ecosystems. Their coexistence creates a landscape in which meat is valuable but rarely uncontested. Scavenging is part of the system. A mammoth that dies from age, injury, winter stress, or accident becomes a temporary centre of activity. Carnivores arrive. Birds strip exposed tissue. Humans may cut meat, break bones for marrow, remove hide, or collect tusk and bone. The sequence is difficult to reconstruct because many agents leave similar marks. Cut marks, tooth impressions, fracture patterns, and the position of bones can suggest what happened, but the evidence remains incomplete. A concentration of mammoth remains may represent hunting, scavenging, natural death, transport by water, or several processes combined. The smallest organisms are less visible but equally important. Insects, soil microbes, fungi, and plants determine how nutrients circulate through cold ground. Decomposition is slow where temperatures remain low, allowing organic matter to persist. Permafrost can lock away roots, carcasses, and carbon for thousands of years. Wind-blown dust adds minerals to soils. Seasonal thaw creates wet surfaces over frozen layers, while dry ridges support grasses and herbs. The mammoth steppe survives through a delicate balance of cold, dryness, grazing, disturbance, and accessible vegetation. It is not eternal. Even during the last glacial maximum, its boundaries shift. A change in snowfall can bury winter forage. A wetter climate can encourage shrubs. A warmer climate can expand trees, but also produce boggy ground and deeper snow that some grazers find difficult. The ecosystem is adapted not merely to cold, but to a particular kind of cold open, windy, relatively dry, and rich in low vegetation. For the humans watching these herds, the landscape is both generous and dangerous. Animals provide nearly everything a mobile community might need, yet they move according to rhythms no person controls. Their trails become maps, their bones become tools, their hides become protection, their absence becomes warning. The great herds make life possible at the edge of the ice, but they also bind human survival across generations through every season of uncertainty to an ecological world whose stability is more fragile than its giants make it appear. The ecological world of the great herds is also a human world, but not one occupied by a single people moving in a single direction. Around the beginning of the last glacial maximum, modern humans are already spread across large parts of Africa, Europe, Asia, and Sahul, while Neanderthals still survive in parts of Western Eurasia. Other archaic lineages have left genetic traces in populations farther east, even where their bones remain almost entirely unknown. The map is crowded with histories that overlap, separate, and sometimes meet again. Ice does not create these populations, but it changes the spaces in which they can endure. In Europe, modern humans and Neanderthals occupy some of the same broad regions during the earlier approach to maximum cold, though not necessarily at the same time or in the same places. by roughly 40,000 years ago, Neanderthal populations have disappeared from the known fossil record well before the coldest interval near 21,000 years ago. Their extinction cannot be explained by the last glacial maximum alone. Climate instability, small population size, competition, assimilation through interbreeding, and regional ecological change may all have contributed. No single explanation fully accounts for their disappearance. What survives genetically shows that they did not vanish without leaving descendants. Most present-day people outside sub-Saharan Africa carry a small proportion of Neanderthal ancestry. That genetic inheritance complicates the boundary between one human group and another. Ancient DNA reveals that modern humans, Neanderthals, and Denisovan-related populations exchange genes at several points. Denisovan ancestry is especially significant in parts of Oceania and in some Asian populations, though the physical record of Denisovans remains remarkably sparse. Their known remains come from only a few sites, and their full geographical range is still debated. By the time the last glacial maximum takes hold, their genetic legacy is already moving through modern human populations whose ancestors crossed Asia and reached Sahul. The people facing glacial conditions are therefore not biologically isolated from the archaic humans who came before them. They carry fragments of those encounters within their own bodies. Still, genes do not provide a complete map of migration. Population histories inferred from DNA must be compared with archaeology, fossils, geography, and climate. A genetic contraction may indicate fewer surviving lineages rather than a total regional collapse. An apparent expansion may reflect later population growth rather than the first arrival in a landscape. Ancient DNA is also preserved unevenly, favouring cold regions and leaving tropical histories especially difficult to recover. Scholars still debate the timing and number of movements across many parts of Asia, Africa, and the Americas because the evidence remains incomplete. At the scale of a continent, apparent emptiness may reflect missing sites, submerged coasts, or generations moving between places that archaeology has not yet securely found. Europe offers one of the clearest examples of demographic pressure. As the climate becomes colder and more unstable, human occupation contracts away from some northern zones. Communities concentrate in refuges such as the Iberian Peninsula, southern France, Italy, the Balkans, and parts of Eastern Europe, although the exact pattern changes through time. These refuges are not sealed shelters where culture simply waits. They are dynamic regions with coastlines farther outward, rivers following different courses, and environments that can support people in some valleys, while nearby uplands remain difficult. Archaeological traditions shift, overlap, and disappear, but labels assigned to stone tool industries do not always correspond neatly to distinct peoples. Farther east, populations occupy the plains and river systems of northern Eurasia despite severe cold. Sites across Siberia show that humans can live at high latitudes before and during the broader glacial period, using fire, tailored clothing, bone tools, and mobile hunting strategies. Some occupations are brief and seasonal. Others suggest repeated return to favoured places. The frozen ground preserves rare objects that would normally decay, but it also creates gaps where erosion or later sediment removes evidence. Human presence in a region may therefore appear intermittent, even when movement through the landscape was more continuous. Beringia becomes both habitat and passage. Its exposed plains link Asia and North America, yet crossing it is not equivalent to walking across a narrow bridge. The region stretches across immense distances, with rivers, uplands, wetlands, and changing zones of vegetation, genetic evidence suggests that ancestral Native American populations experienced periods of isolation and diversification connected to Northeast Asia and Beringia. But the precise location and duration of that isolation remain debated. Ice sheets to the east and south block or complicate movement into the continental interior. Coastal routes may have existed, though many early coastal sites would now lie underwater, while the timing of any interior corridor depends on when ice margins separate and whether the resulting landscape is ecologically usable. Across Africa, the glacial maximum is felt through rainfall, vegetation, and water rather than advancing continental ice. Deserts expand in some regions, forests contract or fragment, and lakes rise or fall according to local hydrology. Human responses vary. Some groups concentrate near rivers, lakes, coasts, or highland refuges. Others adjust mobility and tool use across open grassland or changing woodland. The tropical record does not support one universal population collapse. Different regions show continuity, movement, innovation, or reduced occupation at different times. The coldest global interval becomes many local stories. Sahel provides an equally important contrast. People have already crossed deep water gaps to reach the continent tens of thousands of years earlier. During the last glacial maximum, Australia, New Guinea, and Tasmania form one larger landmass, but they contain deserts, tropical zones, mountains, grasslands, and cold southern environments. Occupation does not simply retreat everywhere. At Dargan Shelter, more than 1,000 meters above sea level, evidence indicates human activity around 20,000 years ago, in conditions once assumed too severe for sustained use. Lower temperatures can reduce evaporation in some regions, maintaining water balance even when rainfall decreases. Archaeology therefore challenges the idea of continent-wide abandonment. On the Tibetan Plateau, charcoal and other traces suggest human activity under cold, windy, oxygen-poor conditions during the glacial maximum. Whether every occupation was permanent, seasonal, or linked to specialized movement remains uncertain, but the sites reveal that altitude is not an absolute barrier. Biological inheritance may have helped later high-altitude populations, yet cultural knowledge is equally essential: fire, shelter, route memory, social cooperation, and familiarity with scarce resources. Humanity at the edge of the ice is not defined by one heroic conquest of cold. It is defined by repeated adjustments, failed routes, remembered refuges, exchanged genes, and decisions made within landscapes that never remain still. Some populations contract, some endure, some merge with others and lose their separate identity. The strongest evidence does not show people defeating the glacial world. It shows them learning, region by region, how long they can remain within it. The limits of endurance are set inside the camp. Out on the plain, cold appears as distance, wind, and frozen ground. But survival is decided in smaller spaces under a rock overhang, beside a hearth, inside clothing stitched from hide, and around stores of food that must last after the herds have moved on. The last glacial maximum does not reward strength alone. It rewards preparation, memory, and the ability to turn animal bodies, stone, wood, bone, fiber, and fire into a shield against a climate that strips heat away. Shelter begins with location. A cave can block wind and hold warmth, but caves are not always safe, dry, or available. Some flood seasonally. Others accumulate smoke or attract bears and hyenas. A deep chamber may be too dark for work, while the entrance may be exposed to drifting snow. People often choose rock shelters, valley edges, river terraces, or low rises with access to water, fuel, stone, and migrating animals. The best place is rarely dramatic. It is the place where a fire can be maintained, runoff drains away, and the surrounding ground can be watched. In open country, shelters must be built. Archaeological traces are difficult to interpret because skins, poles, brush, and cordage decay, leaving only stones, post holes, stains, hearths, and patterns of debris. Some sites suggest circular or oval dwellings anchored by heavy bones or stones. Mammoth bones have been found arranged in ways that may have supported structures, especially in Eastern Europe, though scholars still debate whether every bone concentration represents a house, a windbreak, a ritual arrangement, or a mixture of activities. What survives in the records suggests variety rather than one standard Ice Age tent. The roof may be hide stretched over wood, antler or bone supports, with grass or brush used for insulation. Snow itself can reduce heat loss when banked around an outer wall, provided ventilation remains open. Entrances may face away from prevailing winds. Sleeping areas are raised or layered with hides, vegetation, or other material to reduce contact with frozen soil. Even a modest shelter can transform conditions by slowing airflow. It does not need to become warm by modern standards. It only needs to preserve enough body heat for rest, tool-making, care, and recovery. Fire is central, yet fire is never automatic. Fuel can be scarce on open steppe. People collect branches from woodland pockets, driftwood along rivers, dwarf shrubs, dry grass, bone, and animal dung. Bone burns poorly by itself unless dry and combined with other fuel, but fat-rich fragments can extend a fire. Dung can smoulder steadily where wood is limited. Different fuels produce different heat, smoke, sparks, and ash. And knowing how to combine them is a form of technology as important as shaping stone. A hearth warms, cooks, dries, illuminates, discourages some predators, and creates a place around which work becomes possible after dark. It also carries risk. In a confined shelter, smoke irritates eyes and lungs. Sparks can damage hides. Fuel must be gathered before exhaustion, or bad weather makes the task dangerous. Ash and charcoal preserved at archaeological sites show repeated maintenance, old material swept aside. New fires placed in familiar spots, stones cracked by heat, and activity zones forming around the flame. The hearth is not merely a symbol of community. It is a machine requiring constant labour. Clothing allows that machine to move with the body. A loose hide offers protection, but tailored garments are far more effective because they trap layers of air close to the skin. Stone and bone tools make this possible. Scrapers clean and thin hides. Awls pierce holes. Eyed needles, known from Upper Paleolithic contexts, permit finer stitching with sinew or fibre. Clothing can be layered inner garments for insulation, outer hides for wind resistance, fitted leggings, footwear packed with dry plant material, mittens, hoods, and wraps. Direct evidence is rare because textiles decay, but tools wear patterns, ornaments, and ethnographic comparisons support the importance of carefully constructed clothing. Maintaining those garments is continuous work. Wet fur loses insulating value. Seams split. Footwear wears through against ice and stone. Hides must be cleaned, softened, smoked, stretched, and repaired. The lesser-known truth of cold adaptation is that success may depend less on spectacular hunting than on quiet maintenance repeated every day. A broken needle, a wet boot, or an exhausted fuel supply can become more dangerous than the absence of a weapon. Food presents another balance between abundance and uncertainty. Large animals provide meat, fat, marrow, organs, hides, tendons, and bones. But a successful kill creates an immediate logistical problem. A carcass must be butchered before predators arrive or weather changes. Valuable parts are selected according to transport distance and need. Meat can freeze naturally, dry in cold air, smoke near a hearth, or be stored in protected places. Though preservation methods leave ambiguous archaeological traces, fat is especially important because very lean meat cannot meet all human energy needs. Marrow, brain tissue, and fatty organs may therefore be prized even when muscle meat remains plentiful. Hunting strategies vary with prey and terrain. People can intercept reindeer at crossings, drive animals toward narrow passages, approach horses across open ground, or exploit weakened individuals during difficult seasons. Projectile points, spears, throwing devices, traps, and coordinated movement increase effectiveness. Yet not every bone assemblage proves a dramatic communal hunt. Some animals are scavenged, some trapped naturally, and some remains accumulate over many visits. The evidence remains incomplete, and caution is necessary whenever a site appears to tell a perfect story. Plants continue to matter even in cold environments. Roots, seeds, berries, inner bark, greens, and nuts may supplement animal foods where season and habitat allow. Plant remains preserve poorly, making their contribution easy to underestimate. Coastal and riverine communities can use fish, shellfish, birds, and aquatic mammals. In tropical and subtropical regions, human diets may remain broad despite global cooling. The Last Glacial Maximum does not produce one universal menu any more than it produces one universal climate. Behind every shelter and meal lies cooperation, fuel gathering, hide preparation, cooking, tool repair, route planning, and food sharing spread risk across a group. Knowledge is held socially where water remains open, which valley collects snow, which wood burns slowly when herds pass, and how to recognize weather that will close a route. People survive not because they are untouched by cold, but because no one skill stands alone. Shelter without fuel fails. Fire without food weakens. Hunting without clothing limits movement. Clothing without repair decays. The camps left behind may appear sparse stone flakes, broken bones, patches of ash, but they represent systems of labor woven tightly together. In that quiet organization lies the real technology of the Ice Age, not a single invention, but the disciplined conversion of a hostile landscape into a place where another night can be endured. Movement across the glacial world rarely follows the straight lines drawn on a modern map. The lowest route may be buried beneath ice. The broadest plain may contain no water. A coastline can offer food yet end at a channel too deep to cross. Human travel depends on corridors that open and close with climate, sea level, animal migration, and local knowledge. During the Last Glacial Maximum, lowered oceans create vast new landscapes, but they do not make movement simple. They replace familiar barriers with unfamiliar ones. Beringia is the most famous of these exposed regions. With sea level far below the present, northeastern Asia and northwestern North America become joined across a territory wider than many modern countries. It is a broad region of valleys, uplands, wetlands, and cold steppe. Mammoths, horses, bison, and other animals move through parts of it, while human groups occupy or traverse the broader region. Yet Beringia is also bounded by ice and ocean. To the south and east, the Laurentide and Cordilleran ice sheets obstruct access into much of North America. Along the Pacific margin, glaciers descend toward a coastline displaced far seaward from the one visible today. The timing of routes beyond Beringia remains a central debate in the peopling of the Americas, and the interior passage between the great ice sheets eventually opens, but a gap on Eap is not automatically a usable corridor. Plants, animals, fresh water, and stable ground must return before people can travel through it safely. Some evidence suggests that the corridor became viable only after the earliest widely accepted human presence farther south. A Pacific coastal route may have offered an earlier alternative, with boats or shoreline movement linking productive habitats. Much of that ancient coast is now underwater, so the archaeological record is incomplete. Movement likely depended on changing opportunities along more than one edge of the ice. Across western Eurasia, glacier margins and periglacial plains create a different network. Rivers descending from the ice may be dangerous, braided, and unstable, but their valleys guide travel through open country. The Danube corridor links central and southeastern Europe. Mountain passes through the Alps and other ranges open or close according to snow and glacier extent. Southern refuges in Iberia, Italy, the Balkans, and the Black Sea region support repeated occupation. While northern zones are visited when conditions permit, people do not simply retreat south and remain there. Archaeological sites suggest pulses of expansion, contraction, and return, shaped by prey, fuel, raw materials, and the shifting edge of habitable land. The exposed floor of the North Sea forms a broad plain connecting Britain to continental Europe. Rivers cross this country, later known by the modern name Doggerland, though its glacial landscapes differ from the wetlands that develop after warming begins. During the coldest stages, parts are dry, windy, and sparsely vegetated. Other areas hold channels and low basins. Britain is not yet an island in the modern sense, but ice covers or constrains much of the north and west. Movement into southern Britain depends on the changing balance between ice, open plain, and resources. Farther south, the Mediterranean coastline lies beyond its present position. Coastal plains widen, islands enlarge, and some channels shrink. Yet many crossings still require watercraft. Lower sea level does not erase deep basins. Coastal routes may offer fish, shellfish, birds, plants, and sheltered microclimates, but sites associated with them are especially vulnerable to later drowning. The modern shoreline preserves only part of that human geography. In Southeast Asia, the Sunda Shelf becomes a subcontinent. The Malay Peninsula, Sumatra, Java, Borneo, and surrounding lands are linked across enormous lowlands cut by river systems. Tropical forests respond to cooler and often drier conditions by changing distribution and composition. While open habitats expand in some areas, people can move across ground now covered by the Java Sea and South China Sea, following rivers toward coasts hundreds of kilometers from their modern positions. Yet Sunda remains separated from Sahul by Wallacea, a region of islands and deep channels that never becomes dry land. The crossing into Sahul retains its extraordinary importance. Humans had reached Australia and New Guinea long before the Last Glacial Maximum, which means their ancestors had already made deliberate sea crossings. During the Glacial Maximum, Sahul becomes larger as Australia, New Guinea, and Tasmania are connected by exposed shelves. The Gulf of Carpentaria is transformed into a broad lowland with lakes, rivers, and seasonal wetlands at different times. Bass Strait becomes the Bassian Plain, linking Tasmania to mainland Australia. These are habitable countries supporting routes and communities whose traces now lie beneath water. Travel within Sahul is governed by water as much as distance. Cooler temperatures reduce evaporation in some regions, helping lakes, springs, and soils retain moisture despite lower rainfall. Elsewhere, aridity intensifies. People move between dependable water sources, uplands, river valleys, and coasts. Evidence from Dargan Shelter shows that high-elevation country in southeastern Australia is used around 20,000 years ago. It demonstrates that cold uplands are part of the known world rather than absolute barriers. High-altitude movement also appears on the Tibetan Plateau. Charcoal and artifacts at sites such as Peng Bu King suggest activity during the glacial maximum under severe cold, wind, and low oxygen. Whether visits are seasonal or longer term remains debated. The route demands knowledge of fuel, shelter, water, and the physical effects of altitude. Mountain corridors can provide prey and raw materials, but storms can close them quickly. What looks empty from below may be crossed repeatedly by people leaving faint traces. In South America, the Andes divide environments with dramatic force. Patagonian ice shapes winds and precipitation, making western and eastern routes profoundly different. Farther north, high valleys, intermontane basins, river systems, and Pacific coastal plains offer contrasting paths. The continental shelf extends outward along parts of the coast, yet steep terrain and deserts limit easy movement. In the tropics, forest corridors, savannas, and rivers shift with rainfall. Human responses vary region by region, and no single migration model captures them all. Every exposed plain carries the possibility of a lost archive. Camps beside ancient estuaries, boat landings, fishing places, and river crossings disappear as the ice later melts and seas return. The surviving map favours caves, uplands, and inland terraces. It makes ancient people appear more terrestrial, more cave-bound, and perhaps less mobile than they were. The lowered world opens routes across continents, but its most travelled paths are often the ones least likely to survive. Movement during the last glacial maximum is not a march across empty space. It is navigation through a living network of herd trails, water sources, coastlines, passes, and remembered shelters. Some corridors last for generations, others vanish within a lifetime. To travel successfully is to understand not merely where the land lies, but when it can be crossed. The routes that can be crossed leave another kind of trace behind, not in the shape of a road, but in images, objects, and carefully arranged spaces, in caves, shelters, camps, and open-air sites. People living through the last glacial maximum create marks that do not feed a fire, sharpen a spear, or block the wind. They paint animals on stone, carve figures from bone and ivory, pierce teeth and shells for ornaments, shape beads, engrave patterns, and place objects where their practical use is difficult to explain. These acts do not stand outside survival. They reveal how survival is made meaningful. The most famous images lie deep inside caves in Western Europe, where walls carry horses, bison, lions, rhinoceroses, mammoths, deer, and signs whose meanings are now lost. Some paintings date to periods before the last glacial maximum, others to the colder millennia within and around it, and still others to later phases. Cave art is therefore not one style created at one moment. It is a long and changing tradition. The darkness itself matters. Many chambers are far from daylight, reach through narrow passages, steep drops, and uneven floors. Lamps fueled by animal fat, torches, and small hearths make these visits possible. Smoke stains, footprints, charcoal, and broken lamp remains show that entering the cave is a deliberate undertaking. The artists do not simply copy what they see, they use cracks, bulges, and curves in the rock to give bodies volume. A natural ridge becomes the back of a bison. A hollow suggests an eye. Mineral pigments produce reds, yellows, blacks, and browns, while engraving adds lines that appear only when light moves across the wall. Some figures overlap others made generations earlier. In certain chambers, dangerous predators appear more often than the animals most commonly eaten. This weakens any simple claim that cave art is merely a record of hunting. Scholars still debate whether the images relate to ritual, teaching, storytelling, altered states, social identity, seasonal gathering, or combinations of purposes that changed over time. The caves preserve only what geology protects. Art may also have covered hides, wood, bark, bodies, clothing, and structures, but those surfaces rarely survive. Portable objects offer glimpses of this missing world. Mammoth ivory is carved into animals and human forms. Bone and antler carry repeated lines, cross-hatching, notches, and curves. Flat stones bear engravings that can be seen only under careful light. Some objects are small enough to travel, suggesting that images and symbols move with people across the landscape rather than remaining fixed in one place. Among the most striking objects are female figurines, often grouped under the modern label Venus figures. They vary greatly in size, style, material, and detail. Some emphasize breasts, abdomen, hips, or buttocks. Others are slender, abstract, or faceless. Their meaning is uncertain. Popular explanations have described them as fertility symbols, goddesses, ideals of beauty, self-portraits, or teaching objects, but no single interpretation accounts for their diversity. The name itself is misleading because it imports a much later classical idea into the Ice Age. What survives suggests that human bodies carried symbolic importance, but the exact stories attached to them remain beyond recovery. Personal ornament is more common and perhaps more revealing than spectacular sculpture. Beads made from shell, bone, ivory, stone, and animal teeth appear in patterns that require time and skill. Shells may travel far inland, showing exchange or long-distance movement. Perforated fox teeth, deer canines, and pendants can be sewn onto clothing or worn as necklaces. Their arrangement may communicate age, affiliation, status, achievement, family connection, or something less easily translated. Because clothing itself decays, beads sometimes preserve the outline of decoration long after the garment has disappeared. Color also travels. Red ochre appears at habitation sites, on tools, on ornaments, and in some burials. It can be used as pigment, hide treatment, adhesive ingredient, or body decoration, so its presence is not automatically ceremonial. Yet people collect it, grind it, transport it, and sometimes select particular shades or mineral sources. Black pigments come from charcoal or manganese compounds. Producing and applying these materials requires knowledge of geology as well as visual intention. A painted wall begins with finding the right stone in the wider landscape. Music may also be present, though the evidence is fragile. Flutes made from bird bone and mammoth ivory are known from earlier Upper Paleolithic contexts. demonstrating that complex musical instruments already exist before the coldest phase. During the long glacial period, percussion, clapping, voice, rattles, and instruments of wood or skin may have accompanied gatherings without leaving identifiable remains. Some decorated caves contain chambers with unusual echoes, leading researchers to explore links between acoustics and image placement. The pattern is intriguing, but it does not prove that every painted chamber served as a performance space. Burial adds another layer. Not every dead person received a formal grave, and many graves never survive or are never found. Those that do can include ochre, beads, tools, animal parts, or carefully positioned bodies. Such treatment shows that communities sometimes invest substantial labor in remembrance, even under demanding conditions. The meaning of grave goods is uncertain. They may express identity, grief, belief, social bonds, or practices that do not fit modern categories. It is safer to see burial as evidence of relationship than as a direct map of religion. Art also records the environment selectively. Mammoths, horses, and bison are recognizable, yet plants are rarely depicted in the same obvious way. Landscapes themselves are seldom shown as complete scenes. Human figures are less common and often more abstract than animals. Hands appear as prints or stencils, sometimes made by blowing pigment around fingers pressed to the wall. These impressions are immediate and haunting because they preserve scale and gesture without revealing the individual. Attempts to identify age or sex from hand proportions remain uncertain, and simple conclusions exceed the evidence. The lesser-known surprise is how much planning these images require. Pigments must be gathered, tools prepared, lamps fueled, routes remembered, and difficult chambers entered safely. Some walls are revisited across centuries. This means that caves can function as places of inherited memory, where later visitors encounter marks left by people they never knew. The act of returning binds generations to a landscape in a way that hunting debris alone cannot show. Under the pressure of cold, symbolic life does not shrink into silence. It becomes mobile, layered, and deeply social. A bead crossing hundreds of kilometers, an animal emerging from a rock curve, or a hand outlined in pigment reveals people doing more than enduring winter. They are locating themselves within herds, places, ancestors, and unseen meanings. The ice narrows the habitable world, but inside that narrowing space, imagination continues to widen it. That widening may itself have been one of survival's essential tools. Imagination widens the human world, but survival still depends on geography. During the coldest millennia, some places offer a better chance than others. Valleys sheltered from strong winds, coastlines moderated by water, river basins with dependable fuel, slopes facing the sun, and pockets where trees endure after forests retreat elsewhere. These are often called refuges, though the word sounds more peaceful than the reality. A refuge is not necessarily warm, abundant, or safe. It is simply a region where life remains possible when surrounding landscapes become harder to occupy. In southern Europe, the Iberian Peninsula, southern France, Italy, and the Balkans preserve combinations of open grassland, woodland pockets, caves, rivers, and coastal plains. Human populations do not gather in one continuous southern belt. They cluster unevenly, abandon some areas, revisit others, and maintain connections across corridors that change with climate. Iberia contains cold interior plateaus, as well as milder coastal zones. Italy is divided by the Apennines, with regional differences in rainfall and access. The Balkans connect Mediterranean, continental, and Black Sea environments, making them both refuge and passage. Even here, the archaeological record is patchy, and apparent population centres partly reflect where caves and sediments preserve evidence best. Trees matter disproportionately in these landscapes. Pollen records show that pine, birch, juniper, oak, and other species survive in scattered locations rather than disappearing entirely from glacial Europe. A grove protected in a valley provides firewood, handles, poles, bark, edible resources, and cover for animals. It also preserves soil and moisture. These wooded pockets become biological reservoirs. When the climate later warms, forests expand from multiple surviving populations, not from one southern source. Genetic studies of plants and ancient pollen support a history more complex than the old image of forest retreating to a few isolated corners. Along Atlantic and Mediterranean margins, lower sea level creates broad coastal lowlands. Some are exposed to cold winds, while others benefit from estuaries, lagoons, shellfish beds, fish runs, waterfowl, and relatively stable temperatures. Many attractive places now lie underwater, making coastal refuge difficult to measure. Surviving inland sites may exaggerate the importance of caves and large game hunting, because stone shelters preserve better than camps once built beside vanished shorelines. What survives suggests that coast, river, and upland often formed one seasonal system. Farther east, the plains north of the Black Sea and valleys toward the Caucasus support open country populations adapted to severe winters. Major rivers provide orientation, water, fish, wood, and routes through immense terrain. The Caucasus creates sharp ecological contrasts. Snowbound high ground may be inaccessible, yet lower valleys and southern slopes retain woodland and shelter. The region links Europe, Anatolia, the steppe, and Western Asia, allowing people, animals, tools, and ideas to move through a landscape fragmented but not sealed. Siberia appears on glacial maps as a vast field of cold, yet its river valleys create linear refuges across the continent. The Oboskus, Yenisei, Lena, and their tributaries connect uplands, basins, and steppe tundra environments. In winter, frozen rivers can become travel surfaces. In summer, they provide fish, birds, water, and vegetation. Sheltered terraces offer camps above floods. South-facing slopes warm quickly under long daylight. Fuel remains limiting, but driftwood, shrubs, bone, and dung sustain hearths where woodland is absent. Occupation may be intermittent, but repeated return shows that high latitude does not equal permanent emptiness. Southern Siberia and Central Asia contain another mosaic of refuge zones. The Altai, Sian, and surrounding basins combine caves, river valleys, steppe, forest edges, and mountain routes. These regions preserve evidence of multiple human populations across the wider Pleistocene, including modern humans, Neanderthals, and Denisovan-related groups, though their exact overlap during the last glacial maximum remains uncertain. By the coldest phase, modern humans occupy parts of this zone, carrying technologies suited to mobility and cold. Mountains block some weather systems while channeling others, creating local environments unlike exposed plains nearby. Central Asian deserts also change character. Cooler temperatures reduce evaporation, but rainfall shifts unpredictably. Some lakes shrink, others persist, and river-fed oases become crucial. Loess accumulates where dust settles against mountain fronts. Valleys below glaciers receive seasonal meltwater, though advancing ice can block routes or alter drainage. People depend on chains of reliable places rather than continuous fertile land. A route survives in memory as a sequenced spring, shelter, crossing, fuel, pasture, then another source beyond the ridge. On the Tibetan Plateau, refuge does not mean low ground. Evidence of activity during the last glacial maximum indicates that people reached high elevation environments marked by cold, low oxygen, strong ultraviolet radiation, and limited fuel. Charcoal at sites such as Pengbu King shows that fire was maintained there, but it does not reveal whether occupation lasted weeks, seasons, or generations. Biological adaptations associated with altitude matter in later populations, including genetic variants linked to Denisovan ancestry. Yet culture remains indispensable. Clothing, fire, route knowledge, and cooperation make altitude habitable before any single genetic trait can explain the story. East Asia offers broad river systems and coastal plains displaced beyond their modern positions. In northern China, loess landscapes, steppe, river valleys, and sheltered basins create alternating opportunity and stress. Farther south, the Yangtze Basin remains cold and comparatively dry near the end of the glacial maximum, but pollen shows continuing vegetation rather than ecological collapse. The exposed shelf extends the eastern coastline, while rivers cross lowlands later submerged. Caves and inland basins preserve only fragments of populations that may also have relied on coastal resources. In the tropics, refuges operate differently. They can be wetter forest pockets surrounded by open vegetation, highlands with dependable rainfall, river corridors through dry regions, or coasts where marine foods buffer shortages. Research across Africa, Southeast Asia, and South America shows no single tropical response. Some populations shift diet or technology. Some move between ecological zones. Others maintain continuity in places once assumed abandoned. The last glacial maximum changes tropical life profoundly, but does not reduce it to an imitation of the northern ice world. Refuges are not isolated islands of safety. They are connected nodes in networks of movement, exchange, and memory. Their value depends on knowing when they are productive and how to reach the next one. A valley can preserve trees, yet fail during drought. A coast can provide food, yet become dangerous under storms. A cave can shelter people, yet lack nearby fuel. No single refuge guarantees survival. What endures is the network itself, a chain of remembered places held together by paths, seasonal knowledge, kinship, and repeated return. When climate closes one route, another may remain open. When a herd fails to arrive, fish, plants, or smaller animals may sustain a group elsewhere. Life persists not because the glacial world contains hidden paradises, but because people and ecosystems survive in fragments, carrying continuity from one fragment to the next through long seasons of cold and uncertainty. A network of refugees can preserve life, but it does not preserve every population equally. Across the last glacial maximum, some communities remain in regions for generations, others withdraw and later return, while still others disappear from the archaeological record. The pattern tempts simple explanations. Perhaps one group had better tools, another found richer land, and a third was overwhelmed by cold. Yet the evidence rarely supports such clean divisions. Uneven survival grows from many pressures acting together, and a small difference in timing can determine whether a population endures or fades from view. Population size is one of the least visible factors. A community may possess effective clothing, hunting skills and knowledge of the landscape, yet still remain vulnerable if too few people are spread across too great a distance. Small populations face higher risks from ordinary events several poor seasons. An accident that removes experienced hunters, a failed birth rate, the loss of contact with neighboring groups, or the disappearance of a migration route. None of these needs to be catastrophic alone. Combined over decades, they can reduce a regional population below the level needed to maintain exchange, partnerships, and specialized knowledge. Archaeology records this vulnerability indirectly. A layer containing hearths, tools, and animal bones may be followed by centuries of silence. That silence can indicate abandonment, but it can also reflect erosion, poor preservation, a shift to undiscovered camps, or movement toward coastlines now underwater. The absence of artifacts is not proof that people vanished. Still, when many sites across a region show reduced occupation at the same time, demographic contraction becomes plausible. Scholars still debate how closely changes in stone tool traditions correspond to changes in population, because techniques can spread between groups, persist after migrations, or disappear for reasons unrelated to identity. Climate pressure also arrives unevenly. One valley may become colder but retain water and fuel. Another may lose snowfall yet become drier, reducing vegetation and prey. A third may receive deeper winter snow that hides forage from herbivores. Average temperature alone cannot predict habitability. For people dependent on large game, the critical change may be the timing of herd movement. For communities near rivers, it may be ice cover, fish availability, or flooding. In woodland refuges, the decisive factor may be whether trees continue producing nuts, bark, and usable wood. The same global cooling can create opportunity in one place and crisis in another. Mobility helps, but movement has costs. A group that knows several valleys can shift when one fails. A group confined by mountains, ice, desert, or hostile distance may have fewer options. Moving also means abandoning stored food, familiar shelter, quarry sites, and social maps built around known places. New territory may already be used by others. A route remembered from earlier generations can become blocked by glacial advance or emptied of water. Flexibility is not freedom. Every migration depends on information, strength, timing, and reception elsewhere. Social connection may be as important as environmental knowledge. Ornaments made from distant shells, stone transported over long ranges, and similarities in tool design suggest networks beyond individual camps. These connections allow materials, partners, and information to circulate. During scarcity, a distant relationship can provide access to another hunting ground or refuge. Isolation, by contrast, makes local failure more dangerous. A community cut off by expanding ice, altered rivers, or population decline may lose not only trade but the exchange of ideas needed to adapt. Technology can widen options, though it does not guarantee success. Tailored clothing increases the range of cold environments people can enter. Improved projectiles make certain hunts more efficient. Bone needles, antler points, lamps, shelters, and storage practices reduce risk. Yet technologies are systems of knowledge, not objects alone. A needle is useless without prepared thread and skill. A projectile point requires a shaft, adhesive, binding, and practice. If the social group maintaining that knowledge becomes too small or fragmented, complex techniques may be simplified or lost. This does not imply declining intelligence. It reflects the fragile relationship between innovation and population. Dietary breadth offers another advantage. Communities able to combine large game with fish, birds, small mammals, shellfish, seeds, roots, and seasonal plants may withstand fluctuations better than those tied closely to one prey species. But broad diets depend on local ecology and tools. Coastal abundance can buffer inland scarcity, yet many glacial coasts later disappear beneath the sea, concealing evidence of this flexibility. In the tropics, changing forests and savannas encourage strategies unlike those of northern steppe hunters. Research increasingly shows that human responses to the last glacial maximum cannot be reduced to one worldwide decline. Even animal populations survive unevenly. Reindeer expand in some cold regions while other species retreat. Mammoths remain widespread but experience local contractions. Woolly rhinoceroses occupy much of Eurasia, yet never cross into North America. Cave bears disappear before the end of the glacial period in many areas, likely under combined ecological and demographic pressures. Predators dependent on large prey face their own instability. A species may be well adapted to cold and still decline if snow becomes deeper. Vegetation changes, or breeding populations become isolated. Adaptation fits an ecological pattern, not a temperature label. Competition between humans and animals can intensify around concentrated resources, but the record rarely allows precise measurement. People and carnivores seek the same caves, carcasses, and prey corridors. Humans may exclude predators from shelters or claim valuable kills. Predators may make certain valleys more dangerous. However, stories of constant conflict exceed the evidence. More often, competition is indirect, both dependent on herbivores whose numbers shift with climate and vegetation. The disappearance of a regional culture may also conceal continuity. New tool styles can emerge from existing communities rather than invading populations. Migrants can merge with local groups, leaving mixed traditions and genetic signatures. A people may lose a recognizable archaeological identity without suffering extinction. Conversely, material continuity can hide demographic replacement if newcomers adopt local methods. Objects survive more clearly than identities, and the relationship between them remains uncertain. What separates endurance from disappearance is rarely one decisive advantage. It is the interaction of numbers, connections, mobility, diet, technology, landscape knowledge, and luck. A population survives one severe winter because a neighboring valley still holds game. It survives the next because distant relatives arrive with information. Another group, equally skilled, may face the same cold after its roots close and its herds move elsewhere. The glacial record preserves outcomes more readily than choices. It shows where hearths continue, where tools change, and where occupation pauses, but not the hesitations or failed journeys behind those patterns. Uneven survival is mysterious because the people involved are not simply stronger or weaker. They're caught in different versions of the same changing world, separated by distances small enough to cross on a map and sometimes too great to overcome in life. Those distances become even more dangerous when the animals themselves begin to disappear. The end of the Ice Age megafauna is often told as a single dramatic extinction, as though mammoths, rhinoceroses, giant ground sloths, enormous marsupials, and other large species all vanished together under one global cause. The real pattern is slower, staggered, and regionally uneven. Some populations decline during the last glacial maximum. Others survive thousands of years beyond it. Certain species disappear from one continent while close relatives persist elsewhere. What looks like one mystery from a distance becomes many overlapping extinctions when examined closely. Climate is an obvious force, but climate does not kill by temperature alone. Large herbivores depend on vegetation, snow conditions, water, migration routes, and enough connected habitat to maintain breeding populations. A mammoth can tolerate extreme cold, yet struggle when cold grassland turns into wetter tundra, shrubland, forest, or bog. Reindeer can survive low temperatures but may lose access to forage beneath deep or ice-crusted snow. Woolly rhinoceroses flourish in dry open steppe and decline where the ecological system contracts. The crucial change is often not warming itself, but the reorganization of landscapes that warming, moisture, and changing seasons produce. During the last glacial maximum, suitable habitats can become fragmented even while cold conditions remain widespread. Ice sheets block movement, deserts expand or shift, mountain glaciers separate valleys, river systems alter course. Populations once connected across broad steppe become divided into smaller groups. Genetic exchange falls. Local disasters become harder to absorb. A herd cut off in a shrinking refuge may continue for centuries and still be moving toward extinction, because too few animals remain to recover from poor reproduction, disease, or several difficult winters. This vulnerability is especially severe for large mammals. They tend to mature slowly, produce fewer offspring, and require wide territories. Their size helps them endure cold and travel long distances, but it also demands enormous quantities of food. A small predator population can rebound quickly after a favorable season. A mammoth population cannot. Even modest increases in adult mortality may matter when replacement is slow. The disappearance of a few breeding females each year can alter the future of a herd long before the final animals vanish. Humans enter this problem as another force, but not as a simple army of extermination. Archaeological sites show that people hunted large animals, butchered carcasses, used bones and ivory, and sometimes returned repeatedly to migration corridors. In regions newly entered by humans, animals unfamiliar with human hunting strategies may have been especially vulnerable. Yet direct evidence of mass killing is uncommon, and many carcass sites have ambiguous origins. Cut marks do not always prove that people caused death. A spear point found near bones may be unrelated. Natural traps, drought, starvation, river transport, and scavenging can create assemblages that resemble hunting sites. The absence of abundant kill evidence does not remove human influence. Small populations of hunters can affect slow-breeding animals without leaving vast archaeological deposits, repeatedly targeting young adults, females, or animals concentrated at water crossings may have consequences disproportionate to the number killed. Humans also compete for caves, alter fire regimes, disturb migration routes, and remove carcasses that would otherwise feed predators and scavengers. These effects are difficult to quantify, especially across landscapes now eroded or submerged. No single explanation fully accounts for the timing. In Australia and Sahul, many large-bodied animals disappear well before the coldest phase of the last glacial maximum, making the peak glacial climate an inadequate cause by itself. Human arrival, long-term aridification, changing fire patterns, and ecological interactions have all been proposed. Scholars continue to debate the chronology, because dates differ among sites, and some fossils were redeposited long after death. The strongest interpretations avoid turning uncertainty into certainty. They ask whether human pressure and environmental change acted together rather than demanding one culprit. In Eurasia, the woolly rhinoceros disappears near the end of the Pleistocene after surviving repeated earlier climate oscillations. Its decline appears closely tied to the collapse of dry steppe environments, though human hunting may have added pressure in some regions. Mammoths persist longer, surviving on remote northern islands after mainland populations contract. These island survivors show that extinction is not immediate once climate changes. Small populations can endure where suitable vegetation remains and human contact is limited, but isolation also narrows their genetic and ecological options. North America presents another complicated sequence. Mammoths, mastodons, giant ground sloths, horses, camels, American lions, and many other large animals disappear near the end of the Pleistocene, largely after the last glacial maximum rather than at its deepest cold. Rapid warming, altered rainfall, vegetation change, fire, human expansion, and the collapse of ecological relationships all overlap. The extinction of herbivores removes prey from predators and changes grazing pressure on plants. The loss of predators may alter herbivore behavior before those herbivores disappear. Extinction spreads through a network rather than moving species by species in isolation. Disease has occasionally been proposed as a broad explanation, but evidence is weak. A pathogen capable of crossing many unrelated species while leaving others untouched would require assumptions unsupported by the fossil record. Catastrophic impacts and other popular theories have also been suggested for some extinction pulses, yet they do not match the regional timing well enough to replace climate and human ecology as the main framework. Such ideas remain disputed because a dramatic mechanism is not automatically a better one. There is also the problem of survival. If humans inevitably destroy every large animal they encounter, then bison, reindeer, moose, elephants, and many other species should not have persisted. If climate alone determines extinction, species that survived earlier glacial cycles should have endured the final transition as well. The survivors show that outcomes depend on habitat flexibility, reproduction, geography, behavior, and the intensity of human pressure. Some animals retreat into forests or mountains, some shift diet, some remain numerous enough to withstand hunting, others are trapped by specialization. The extinction debate therefore resists a verdict because the causes interact. Climate changes the habitat. Fragmentation reduces population resilience. Human hunting adds mortality. Fire and competition reshape local ecosystems. Slow reproduction prevents recovery. Chance determines which refuge fails first. By the time the final animals disappear, the process may have been unfolding for millennia. What vanishes is more than a collection of giants. Their loss changes vegetation, nutrient movement, predator communities, and the routes people once followed. Grasslands become less heavily grazed, shrubs and trees expand in some regions, bones, tusks, and hides become rarer materials. Stories and images preserve animals no longer seen beyond memory. The empty spaces they leave behind are ecological evidence, a reminder that extinction is seldom one blow, and more often the final stage of a world whose connections have already begun to break. The connections have not yet broken everywhere when the glacial world reaches its deepest expression. Around 21,000 years ago, the Great Northern Ice Sheets stand near their maximum combined extent. Sea level lies close to its lowest range, and vast regions experience some of the coldest conditions of the last glacial cycle. Yet even here, at the frozen peak, the world does not pause. Ice advances in one basin while thinning in another, ocean currents continue beneath expanded sea ice. Mountain glaciers reach local maxima at different moments. The last glacial maximum is not a single date carved into the climate, but near this interval its pressures overlap with unusual force. Over North America, the Laurentide ice sheet forms a continent-sized mass rising thousands of meters above the land. Its frozen surface resembles a high plateau, smooth at distance but broken by crevasses, ridges, melt features, and zones of fast-moving ice. Snowfall feeds some sectors more effectively than others. At the margins, glaciers grind across bedrock, transport debris, and build moraines that mark advances and pauses. Farther west, Cordilleran ice fills mountain valleys and spreads into adjacent lowlands. Where the two systems approach, routes between the Pacific and the interior narrow or disappear, creating barriers not only of ice but of cold desert and unstable meltwater terrain. Across northern Europe and the Arctic seas, the Eurasian ice complex dominates Scandinavia, the Baltic Basin, parts of Britain and Ireland, and regions now covered by shallow water. Its height changes atmospheric circulation across the continent. Cold air spills southward. Storm tracks bend around the frozen mass. Some sectors receive enough snow to maintain growth, while others remain surprisingly dry because cold air carries little moisture. An ice sheet can be enormous and still contain interior regions with low annual snowfall. Its survival depends on accumulation exceeding loss over long periods, not on constant blizzards. The dry atmosphere is one of the defining features of the glacial maximum. Cold oceans evaporate less water. Expanded sea ice reduces exchange between ocean and air. Continental interiors become arid, and sparse vegetation exposes sediment to wind. Dust concentrations in Greenland ice rise far above later Holocene levels. Individual grains reveal changing source regions and transport pathways, suggesting powerful shifts in circulation. Dust crosses Asia, Europe, and the North Atlantic, settling on snow, grass, lakes, and marine surfaces. It can fertilize ecosystems by supplying minerals, but it also signals landscapes under stress, where soil is bare and rainfall is too weak to clear the air efficiently. Loess accumulates in thick blankets across parts of Eurasia and North America. These fine sediments preserve the work of countless windstorms, each carrying particles from floodplains, glacial outwash, deserts, and exposed shelves. In places, dust falls onto permafrost and becomes incorporated into frozen ground rich in organic carbon. Much later, thaw will release part of that stored carbon, but during the maximum it remains locked beneath cold soils. The ground itself becomes an archive of atmospheric dryness. Sea level remains near its lowest range, roughly 100 to 125 meters below the present, depending on region and reconstruction. Along the Atlantic coast of Africa, evidence indicates that relative sea level may continue falling through much of the interval from about 27 to 19,000 years ago. The ancient shoreline lies far beyond the modern coast, exposing plains crossed by rivers and occupied by ecosystems now lost beneath the ocean. In Patagonia, the Atlantic shelf widens dramatically, altering tides and coastal environments. The sea has not simply retreated, it has created new landscapes with their own currents, estuaries, and seasonal rhythms. The oceans remain active beneath the cold surface. Research on North Atlantic deep water suggests that relatively warm and salty deep water formation persists during the last glacial maximum, with some source waters only modestly cooler than modern equivalents. This does not mean the ocean is warm. It means the circulation is more complex than a frozen stagnant basin. Dense water still sinks. Heat and salt still move. Regional currents influence sea ice and the stability of nearby ice sheet margins. The planet at maximum glaciation remains dynamic from the abyss to the atmosphere. On land, ecological space is compressed and rearranged. The mammoth steppe reaches great extent across northern Eurasia and Beringia, but even this signature ecosystem is fragmented by mountains, glaciers, deserts, and local moisture. Productive grasslands coexist with sparse tundra, cold deserts, river wetlands, and woodland refuges. Winter snow depth becomes critical. Thin, windswept cover allows grazing animals to reach forage. Deep snow or hard ice crust can exclude them from otherwise suitable ground. A small change in storm pattern can alter the carrying capacity of a region without changing its average temperature dramatically. In Europe, pollen records show severe winter cooling and dryness, yet trees survive in sheltered places. The glacial maximum does not erase woodland so much as break it into scattered pockets. Around the Mediterranean, local topography creates sharp differences over short distances. Northern Africa and the Middle East experience shifting rainfall and vegetation, rather than one uniform desert expansion. Across Australia, average temperatures are lower, but reduced evaporation maintains moisture in some regions, helping explain continued human occupation. The tropics remain ice-free at low elevation, though forests, savannas, rivers, and seasonal rainfall reorganize profoundly. Human communities live within this restricted but varied world. Some northern territories are abandoned or visited only briefly. Refuges become more important, and social networks may stretch across greater distances as neighboring populations thin. Yet people remain in high, cold, and seemingly marginal places. Activity at Dargan Shelter in southeastern Australia around 20,000 years ago shows occupation above 1,000 metres. Evidence from the Tibetan Plateau indicates human presence under severe cold and low oxygen. These sites do not prove that every harsh environment supports permanent settlement, but they show that the boundary of habitability is cultural as well as climatic. The glacial extreme is therefore not a moment when life stops. It is a moment when margins become narrow. Animals depend on precise combinations of snow, grass, and movement. Humans depend on roots, fuel, clothing, food storage, and cooperation. Forests persist where slopes and moisture protect them. Oceans circulate beneath expanded ice. Dust connects dry interiors to distant seas. Every system continues, but with less room for failure. From the surface of an ice sheet, the world might appear conquered by cold. From below, it is still full of motion, pressure, and adjustment. The maximum is not the triumph of stillness. It is the point at which the planet holds the greatest amount of water on land, exposes the widest lost coastlines, and forces living systems into their most compressed patterns. That pressure cannot remain unchanged forever, and beneath the apparent stability, the first conditions of retreat are already beginning to gather. The first signs of retreat do not arrive as warmth everywhere. They begin as imbalances. Summer sunlight increases at high northern latitudes as Earth's orbit changes. Ocean waters carry heat into places where ice sheet margins meet the sea. Snowfall shifts. Some glaciers continue advancing because their enormous mass responds slowly, while nearby sectors thin from below or lose more ice each summer than winter can replace. The frozen world does not end with a single thaw. it begins to loosen through a chain of changes that unfold at different speeds. This distinction matters because the last glacial maximum is an interval, not a switch. Around 19,000 years ago, global ice volume remains immense, yet major components of the glacial system are already becoming unstable. Recent research on the Eurasian ice sheet suggests that the southern Nordic seas began warming during the late maximum, before the largest phase of deglaciation was fully underway. Increasing summer insolation helped alter ocean conditions, and those oceanic changes delivered heat toward the marine margins of Fennoscandian ice. The collapse that followed was not caused by sunlight alone or by the ocean alone. It emerged from their interaction with an ice sheet sensitive to changes at its edges. Marine-based ice is particularly vulnerable. Where an ice sheet rests on ground below sea level, warm water can reach beneath floating shelves or grounding zones and increase melting from below. As the margin retreats into deeper basins, the ice can become harder to stabilize. Calving releases more icebergs. Fresh water enters the sea. Currents shift in response, yet even this process is uneven. One fjord can retreat rapidly, while another remains pinned against shallow bedrock. The shape of the seabed, the direction of currents, and the thickness of the ice determine how quickly local collapse proceeds. Across North America, the Laurentide ice sheet also begins a long transformation. Its southern margins withdraw from some regions while large interior domes remain. Meltwater collects in lakes trapped between ice and rising land. Rivers change direction as old outlets open and close. Some lakes drain gradually. Others escape suddenly when an ice dam fails, sending immense floods across valleys and lowlands. These events can be regionally catastrophic, but they should not be confused with one deluge. Deglaciation produces many floods at different times, separated by centuries or millennia. The crust responds after the burden of ice is reduced. Land once pressed downward begins to rise through glacial isostatic adjustment, a process that continues today in parts of Canada and Scandinavia. Around former ice margins, peripheral bulges subside. As a result, local shorelines move according to both rising ocean volume and changing land elevation. In some places, the sea advances rapidly across low plains. Elsewhere, rising ground outpaces the ocean. The modern pattern of raised beaches, drowned forests, submerged valleys, and tilted lake basins records this complicated recovery. Global sea level begins its long rise as meltwater returns to the oceans. The exposed shelves of Beringia, Sunda, Sahul, the North Sea, and Patagonia do not disappear immediately. For thousands of years they remain countries through which rivers flow and people move. Then coastlines begin to migrate inland. A marsh becomes an estuary. A river valley becomes a bay. Low ridges turn into islands before vanishing beneath shallow water. Human communities living on these plains must relocate, often leaving their most important sites where later seas destroy or bury them. The rise is not smooth. Periods of faster melt alternate with pauses, and some episodes produce rapid increases in sea level. Their exact sources and timing remain debated because different ice sheets contribute at different moments. Antarctic, Laurentide, Eurasian, and mountain glacier melt all play roles, while ocean temperature changes affect water volume as well. A single global curve can summarize the trend, but every coast experiences its own sequence of flooding, erosion, sedimentation, and tidal change. Ecological change follows with equal complexity. As temperatures rise and atmospheric moisture increases, shrubs and trees expand into regions once dominated by open steppe. This growth is not automatically beneficial to every species. Mammoths and woolly rhinoceroses depend on broad, dry grasslands, and their habitat contracts as tundra becomes wetter. Snow deepens in some areas, and forests spread. Reindeer shift their ranges. Horses retreat from certain regions but flourish elsewhere. Predators lose prey or follow it into new environments. The mammoth steppe does not vanish in one season. It fragments, leaving isolated pockets that support remnant populations for centuries or longer. Frozen soils also begin to thaw. Permafrost rich in ancient organic matter becomes unstable, and erosion releases sediment and carbon into rivers, lakes, and the atmosphere. Research on northern land carbon suggests that hundreds of petagrams were lost during the transition from glacial conditions, particularly from loess-rich permafrost deposits. Later, expanding peatlands store carbon again, but the first response is often release. The land is not simply greening, it is decomposing, slumping, flooding, and rebuilding its soils under new conditions. Forests spread from multiple refuges across Europe, Asia, and North America, but their advance is interrupted by cold reversals and regional droughts. The most famous of these later disruptions, the Younger Dryas, occurs after the last glacial maximum and near the end of the wider deglaciation. It brings a return to colder conditions around the North Atlantic, though its global expression varies. It is not the cause of the first retreat, nor does it reverse the entire planet to full glacial conditions. Instead, it shows that warming can proceed through abrupt turns rather than a steady climb. Human populations respond to this unstable transition with movement, invention, and loss. Northern territories once buried beneath ice gradually open, but newly exposed ground is initially raw, wet, and poor in soil. Plants, animals, and people colonize it in stages. Former refuges become sources of expansion, yet rising seas erase coastal territories that may have supported dense occupation. Hunting strategies shift as familiar herds decline or move. Fishing, gathering, and the use of woodland resources become more important in many regions. Tool traditions change, but whether those changes reflect migration, local adaptation, or cultural exchange differs from place to place. The end of the last glacial maximum is therefore not the end of hardship. It replaces one set of pressures with another. Ice retreats, but coastlines vanish. Forests return, but open steppe animals lose habitat. Rivers carry more water, but floods and unstable channels reshape valleys. New land opens in the north while old land disappears beneath the sea. The people who endured the cold now face a world changing faster in some regions than inherited memory can easily contain. The long retreat begins with warmth, but it is remembered in movement, ice drawing back from stone, oceans moving over plains, trees advancing across dust, and communities following coastlines that will never stop where they once stood. The coastlines keep moving long after the first great retreat begins. Across the North Sea basin, rivers wander over low plains where fishing grounds, camps, marshes, and hunting routes later vanish beneath the water. In Beringia, tundra steppe narrows as the Pacific and Arctic seas return. Across Sunda, valleys become straits and ridges become islands. Around Sahul, the Bassian Plain, the Gulf of Carpentaria lowlands, and broad coastal shelves are flooded in stages. Patagonia loses immense tracts of exposed land to the Atlantic. These changes do not erase empty geography. They drown inhabited worlds, and because those worlds disappear below modern coastlines, they leave the human story permanently incomplete. The archaeological record therefore favours what remained high and dry. Caves, rock shelters, inland terraces, and upland basins survive where estuaries, beaches, lagoons, and river mouths do not. This imbalance can make Ice Age societies appear more dependent on caves and large mammals than they truly were. Coastal communities may have relied on fish, shellfish, waterfowl, sea mammals, edible plants, driftwood, and predictable tidal environments. Their tools may have included wood, fibre, nets, baskets, watercraft, and other materials that decay easily. When the sea rises, it not only covers sites but reworks them through waves, currents, and sediment. Some traces are buried intact, others are scattered beyond recognition. Underwater archaeology has begun to recover fragments of these lost landscapes, but the task is difficult. Modern seabeds are large, expensive to survey, and often hidden beneath thick sediment. Ancient river channels can be mapped with sonar and seismic methods, while cores reveal pollen, peat, freshwater deposits, and soils formed before inundation. Occasionally, stone artifacts or animal remains are found offshore, yet their original context may be uncertain. A tool recovered from the seabed can prove that people used the exposed shelf, but not necessarily where a camp stood or how long it lasted. The evidence remains incomplete, and much of the most attractive coastal ground may never be reconstructed in detail. The lands that remain above water are transformed as well. Former ice sheet centres rise slowly after the weight is removed. Lakes tilt as one shore rebounds faster than another. Rivers cut new outlets. Glacial debris creates soils that begin thin and unstable, then deepen as plants, fungi, insects, and animals return. Forests spread into regions where dust-rich steppe once supported mammoths and horses. Peatlands form in poorly drained basins. Wet tundra replaces some dry grassland. The ecological world of the Last Glacial Maximum does not simply move northward. It breaks apart, reorganizes, and leaves combinations of species that have no exact modern equivalent. Many of the giants disappear during this transition, but their influence remains written into the landscape. Mammoths once disturbed shrubs, opened ground, moved nutrients, and maintained paths through steppe. Large grazers shaped plant communities through feeding and trampling. Predators structured the behavior of prey. When these animals vanish, vegetation changes partly because climate changes and partly because the old ecological pressures are gone. It is difficult to separate these effects precisely, but the modern tundra and boreal forest are not merely warmer versions of mammoth country. They are ecosystems rebuilt after the loss of major participants. Ancient carbon also enters the New World. As permafrost thaws, organic matter stored in frozen loess and soils begins to decompose or wash into waterways. Large quantities of northern land carbon are lost during deglaciation before later peatlands begin accumulating carbon again. The process links the solid ground to the atmosphere and ocean. It also reveals how glacial landscapes can continue influencing climate after the ice retreats. What appears to be dead frozen Earth is actually a reservoir of ancient biological material, waiting for temperature, water, and microbes to unlock it. Human populations carry other traces forward. Genetic lineages expand from refugees, mix with neighbouring groups, and move into newly available lands. Present-day ancestry preserves faint records of ancient population contractions, separations, and reunions. though genes cannot identify every root or cultural identity. Neanderthal and Denisovan ancestry within modern populations reaches back to encounters before the last glacial maximum. Yet those inherited fragments continue through the glacial world and beyond it. They influence the biology of later people without preserving the names, appearances, languages, or stories of the individuals from whom they came. Some genetic variants prove especially useful in environments shaped by the Ice Age. Adaptations related to high-altitude life on the Tibetan Plateau include ancestry connected to Denisovan-related populations. Although the complete history of selection remains complex, other inherited differences influence immunity, metabolism, skin, and responses to local climates. These are not monuments consciously built by vanished peoples. They are biological traces carried unknowingly across generations. Their survival shows that disappearance is rarely absolute. A population can cease to exist as a distinct group, while parts of its ancestry continue inside others. Cultural inheritance is harder to follow but no less important. Knowledge of sowing, fire, shelter, navigation, hunting, fishing, and seasonal movement does not fossilize directly. It survives when people teach it. The technologies visible in stone and bone are only durable fragments of larger systems involving gesture, memory, language, and practice. When communities move from open steppe into woodland, from inland plains toward new coasts, or from refuges into deglaciated territory, they adapt old knowledge to unfamiliar settings. Some traditions persist. Others are abandoned because the animals, materials, or roots that gave them meaning have disappeared. The end of the glacial maximum also changes how people imagine place. A valley known to generations can become an estuary. A distant ridge becomes an island. A crossing used in winter becomes deep water. Oral memory may preserve accounts of moving shores, but such traditions are difficult to connect securely to specific Pleistocene events. Popular claims often treat every flood story as a direct memory of post-glacial sea level rise. That conclusion exceeds the evidence. Flood traditions can arise from many experiences, including river floods, storms, tsunamis, and later coastal change. Still, the repeated loss of inhabited land must have shaped human memory, even when the original forms of that memory cannot be recovered. By the early Holocene, the planet has crossed out of the last glacial maximum, but the glacial world has not vanished without consequence. Its ice carved the basins of future lakes, deposited fertile loess, redirected rivers, and set coastlines in motion. Its refuges influenced where plants, animals, and people expanded. Its low seas connected lands later separated by water. Its environmental pressures shaped human mobility, cooperation, and innovation. Much of the geography beneath modern civilization was prepared by processes operating when no city, kingdom, or written record existed. Its deepest shadows still lie beneath the waters surrounding us today. The strongest lesson is not that humanity conquered a frozen Earth. The planet was never frozen everywhere, and survival was never one universal triumph. People endured regional differences. Some lived beside continental ice, others crossed cold deserts, tropical forests, high plateaus, or coastal plains that no longer exist. Some populations contracted, some moved, and some remained where older theories expected abandonment. Resilience was real, but uneven, collective, and dependent on ecosystems that could fail. As the last light fades across an exposed plain, the distance between that world and ours feels immense. Yet beneath a modern beach, an ancient river may lie buried in sediment. beneath a northern forest, dust from the mammoth steppe remains in the soil. In the curve of a valley, the passage of ice is still visible. Within living genomes, traces of encounters continue through time. The great sheets once pressed continents downward and held oceans away from their shores. They narrowed forests into refuges, stretched grasslands across vanished countries, and made remembered routes into lifelines. Then they withdrew without a clear boundary between ending and beginning. Water returned, trees advanced, herds changed direction, familiar animals disappeared. People followed the shifting ground, carrying knowledge, tools, relationships, and memories, while leaving other parts of their world behind. Most camps are gone. Their coastlines have no surviving names. The stories spoken beside their fires vanished with the voices that remembered them. What remains is indirect, a hand against stone, charcoal beneath a high shelter, a sharpened point near old bone, pollen sealed in lake mud, dust preserved in Greenland ice, and fragments of ancestry passing through descendants who cannot know their source. Time preserves history unevenly. Stone survives while clothing decays. Uplands remain while coastal plains drown. A glacier can leave a valley visible for ages, while a human life leaves only ash. Great changes can be traced in broad outlines, but small decisions remain unseen, choosing shelter, sharing food, repairing a seam, or abandoning a route before weather closes it. Outside the shelter, wind moves through grass where mammoths once passed. Far away, meltwater finds a new path toward the sea. The ice on the horizon appears motionless, though it is already retreating, grain by grain and season by season. Behind it lies raw ground. Before it lies a coastline that will not remain. Between those moving boundaries, people continue walking. Their footprints fade, but the journey reaches forward through drowned landscapes, altered ecosystems, inherited bloodlines, and every modern shore built from a colder world.